Well, hey guys, welcome to our second class via YouTube. I hope the first week went okay, and I will be posting an area where you can put some feedback out there regarding whether or not this is working for you. So, I found last week that it was much easier to split the lecture up when I was doing my physics class, to split it up into a review video and then a new material video. So I think that's what I'm gonna do. So this first video will be review. So let's just start with a word of prayer. Dear God Almighty, I just come before you humbly today, Lord. Ask your blessing upon this class, even though we're separated physically, Lord. I pray that you would help us feel united over the internet. I pray that you would give me the words to speak and give the students a mind for understanding. Father, in this time of uncertainty, I just want to praise your holy name. Lord, this virus is nothing new to you. You've known about it since the beginning of time. You know the outcome. And I just pray that we could have peace in that, and that you would just protect us, keep us safe, keep our families safe and our homes safe. Father, be with all those who are hurting right now, who need healing. Be with the healthcare workers and the emergency responders and all those who are caught up in this crisis. Father, I just thank you. I thank you even for this rainy day outside, Lord, that you're nourishing the earth, and I just pray that you would be with us in this time. Thank you most of all for your son, Jesus, and it's in his name we pray. Amen. Okay, so we're gonna review the final half of module 13 about heat and energy. And if you remember from last week, the first thing we started discussing is that the calorimeter actually absorbs some of the heat that's given off by the object that's put into it. So we had started our calorimeter problems ignoring the calorimeter, but we're no longer ignoring it. It absorbs some of the heat along with the liquid. Okay, so when we're doing problems, we have to take this into account. Now the reason, well, let me back up. The calorimeter is not made of a pure substance. So specific heat capacities are given for pure substances, elements and such. The calorimeter is not a pure substance. It has many components. So it would be kind of impossible to come up with a specific heat capacity for the calorimeter. So instead, what we do is we come up with the heat capacity. So a calorimeter has a heat capacity. And that heat capacity is measured in joules per degrees Celsius. There's no mass in heat capacity, okay? We look at the calorimeter as a whole, okay? So this heat capacity gives us the heat capacity for the calorimeter as a whole, not per gram. If you remember, specific heat capacity is joules per gram degree Celsius. Instead, heat capacity is just joules per degree Celsius. Mathematically, for the calorimeter, how we calculate it is we say Q, which is our heat, equals C delta T. And you'll notice this time that the C is capital, okay? And that C is our heat capacity for the calorimeter. It's not the same as specific heat capacity. Okay, so these two are very similar in their name, but they are not the same. Specific heat capacity is for a pure substance, and you measure it per gram. Heat capacity is for the calorimeter, and it's just joules per degree Celsius. All of our other variables are the same. Q is our heat, change in temp, we know how to do that. Okay, so Q is our heat, we measure that in joules. Change in temp is the final temp minus the initial temp. We measure that in degrees Celsius. Okay, our heat capacity is joules per degree Celsius. So you'll note when we multiply these two, degrees Celsius cancels out and we're left with joules equals joules, which is what we want. Okay, so let's look at a problem that you had in your homework and just walk through this, if nothing else, to refresh your mind. And if you had any issue with this problem, hopefully it'll help explain it. So we're looking at comprehension check number 9. And it's on page what? Page 402. Okay. So this is a calorimeter problem where we cannot ignore the calorimeter. So we're going to have a metal. We're going to have the liquid inside the calorimeter. And then we're going to have the calorimeter itself. Okay, and let's just list the different things that we know about these three things that we were told in the problem. So it says a 300.0 gram sample of an unknown metal. So already we know the mass of the metal is used in a calorimetry experiment. The calorimeter holds 1,200.0 grams of water, okay? So this liquid we know is actually water, and that's kind of key, we'll see in a minute. Mass is 1,200.0 grams. And it starts off, the water starts off at a temperature of 25.0 degrees Celsius. So our initial temperature is 25.0 degrees Celsius. Okay, the metal is heated to 136.3 degrees Celsius. So the metal's initial temperature is 136.3 degrees Celsius. And then it's dropped in the calorimeter. The experiment ends when the water reaches a temperature of 27.3 degrees Celsius. So the final temperature, 27.3 degrees Celsius. Okay, now I want to talk about these temperatures for a minute before we go on any further. If the initial temperature of the water or liquid inside the calorimeter is 25.0 degrees Celsius, then the calorimeter's initial temperature is that same thing. Okay? The temperatures of these two are always the same. Okay, because they act as a unit. The water is in the calorimeter, all right? So their temperatures are always going to be the same. So if the final temperature of the water is 27.3, the final temperature of the calorimeter is also 27.3. And we know that at the end point, the final temperature of everything is the same. All the temperatures have settled at 27.3 degrees Celsius. Okay, so the water and the calorimeter, those two temperatures are always the same. They act in unison. Their initial temperature is the same, their final temperature is the same. The metal's initial temperature is usually much hotter. That's why we're putting it into the calorimeter to see how much heat it will lose. But its final temperature is the same as the water and the calorimeter. In the end, all three have the same temperature. Okay, so based on the information we have in all of these, we can calculate the change in temperature. Okay, so remember, it's final minus initial. So if you do that math out, the change in temperature here is 109.0 degrees Celsius. The change in temperature for the water is 2.3 degrees Celsius, and obviously the change in temperature for the calorimeter is 2.3 degrees Celsius. okay? So that takes care of all of our initial, final, and change in temperatures. Okay, there was one more sentence in the problem then. It says, if the heat capacity of the calorimeter is 1100 joules per degree Celsius. So our heat capacity of the calorimeter, remember that's the capital C, is 1100 joules per degree Celsius. What is the specific heat capacity of the metal? So this over here is what we're trying to solve. Okay, now there's one more variable that we know, and I'll give you a minute to see if you can figure it out. We know the specific heat capacity of water, right? That's that 4.184 joules per gram degree Celsius. Remember, you're going to need to know this value, okay? So all I've done so far is I've read this comprehension check and I've written down everything that I know about the metal, the water, and the calorimeter. And I know that I'm trying to solve for the specific heat capacity of the metal. So where to start? Okay. So if you think of our equation, we have two equations for heat actually. We have C equals Q equals Cm delta T. And we also have Q equals capital C delta T. Now, if you notice for the water, we have every variable except the heat. So we can start out by analyzing the water, okay, and solving for the heat. So Q equals Cm delta T. Okay, for the water, our C is 4.184 joules per gram degree Celsius. Our mass is 1200.0 grams, and our change in temperature is 2.3 degrees Celsius, okay? And if I do all that math out, I end up with, let's see, what do I end up with? 12,000 joules, okay? And you can see our grams cancel out and our degrees Celsius cancel out. I'm left with joules, which is what I want, okay? So we know that the water gained 12,000 joules of heat or energy, okay? And we know it gained it because this is a positive number. All right, let's look at our calorimeter, the contraption itself. For the calorimeter, we don't look at specific heat capacity, we use just heat capacity. So again, we can calculate the heat that the calorimeter gains by using capital C delta T, all right? And again, I have both of these variables, so I can solve for heat. My heat capacity is 11,000 joules per degree Celsius. My change in temperature is that same 2.3 degrees Celsius. And if I do that multiplication, sorry, this is 1100, not 1000. If I do that multiplication, I end up with 2,500 joules. Okay? My degrees Celsius cancel out. So when the hot metal was dropped into the water in the calorimeter, the water gained 12,000 joules of heat. The calorimeter gained 2,500 joules of heat. So how much was the total heat gain? Well, it's my 12,000 joules plus my 2,500 joules. Okay, and let's look at significant figures here. 12,000 is to the thousands position. This one's to the hundreds position, so I have to report to the least precise position, which is the thousands position. So if I add these together and take significant figures into account, I end up with 15,000 joules. Okay. So the calorimeter and water gained 15,000 joules of heat combined. All right, so that means the metal lost 15,000 joules. Okay, and we write that by saying the Q of the metal equals minus 15,000 joules. Right? If the water in the calorimeter gained 15,000, that had to come from somewhere. It came from the metal. The metal lost 15,000 joules. Okay, so I could go back up here and I could write in my Q is minus 15,000 joules. Okay, so we've looked at the water, we've analyzed the calorimeter, all that's left is the metal. Well, now look, I have every variable that I need to use this equation for the metal except my specific heat, which is what I'm trying to solve for anyway. So if I take Q equals MC delta T, I solve this for C just by rearranging the equation. C equals Q over M delta T. I have all three of these variables, so I can solve for C. So Q is minus 15,000 joules. The mass of my metal is 300.0 grams. And the change in my temperature is negative 109.0 degrees Celsius. Okay, so now you're going to have a negative divided by a negative, so your answer is going to be positive, which we would expect. And if you do the numbers out, the specific heat capacity ends up being 0.46 joules per gram degrees Celsius. And this is your final answer. Okay? So a problem like this, it looks like a lot of work, but just do it piece by piece by piece. Follow the process and you'll get through. So what did I do? I started out by making my 3 different columns and writing everything that I knew about the metal, about the liquid, and about the calorimeter. Then I started by analyzing, in this case, the water, because I had most of my variables. I was just missing heat, which I could calculate. I looked at the calorimeter, same thing. I had most of my variables except the heat, which I could calculate. I then knew that together, if my water and calorimeter gained 15,000 joules, that meant that the metal lost that same amount of heat. Okay? And once I knew my Q here, then I could analyze the metal for the one variable that I didn't know, which was the specific heat capacity. Okay? So hopefully that's been helpful. Okay. Then we went on and we talked about latent heat. And latent heat is the heat that's absorbed or gained during what? Can you fill in the blanks? During a phase change. Okay, so latent heat is the heat absorbed or gained during a phase change. And if you remember the graphs that we looked at some time ago, the y-axis is the temp, the x-axis is the heat. So as something heats up, You know, here maybe it's in its solid phase, then it starts melting. So even though we're adding more heat, its temperature isn't increasing because it's melting here, okay? When everything is done melting, then as we add more heat, the temperature increases until it gets to its vaporization stage. Here, even though, again, we're adding more heat, we're going across on this x-axis, the temperature isn't changing because everything is vaporizing, okay? If you remember, there were two types of latent heat. There's latent heat of fusion and latent heat of vaporization. Fusion is when something is going from a solid to a liquid or from a liquid to a solid. We use the latent heat of vaporization if something's going from a liquid to a gas, or if something's going from a gas to a liquid. This can go either way, okay? So in our case, this would be where we would use the latent heat of fusion. Up here would be where we use the latent heat of vaporization. Okay, mathematically, we show this by saying the heat equals the mass times the latent heat. Okay, so this is heat again, this is mass, and this is our latent heat. Okay, the heat is in joules, the mass is in grams, the latent heat is joules per gram, which makes sense. So at home, you should have done the experiment with the 2 cups of water. One had ice in it, one did not, and then you added boiling water to both cups. And you should have noticed that the cup with the ice stayed cooler than the cup that never had ice in it. Well, why was that? Even when the ice melted, it was still colder. So the reason that was is because some of the heat from the boiling water had to be used to melt the ice. It had to be used here before it could raise the temperature any further, okay? The other cup, there was no phase change. There was no ice to melt, so the heat could immediately start raising the temperature of the water. So hopefully that made sense to you as you did that lab at home. Let's look here at On Your Own 10. Just do a review of On Your Own 10. Okay, you should have this in your homework so you can follow along if you'd like. Just doing it again as a review. And On Your Own 10, we have a sample of ice. Okay, so we have solid ice. 300, the mass is 300.0 grams. The ice is at 0.0 degrees Celsius, and it's converted into water vapor at 100.0 degrees Celsius. And it wants to know how much heat is absorbed in this process of ice going from 0 degrees Celsius to all water vapor at 100 degrees Celsius. And then it tells us our latent heat of fusion is 334 joules per gram. And our latent heat of vaporization is 2,260 joules per gram. Okay, so let's think about this. We're going from solid ice at 0 degrees to water vapor at 100 degrees. So let's draw a little graph here so we can picture what's going on. Okay, so here's our temp again. Here's our heat. Heat's increasing as we move to the right. Here's 0 degrees. Here's 100 degrees. So we're already at 0 degrees, okay? and the ice is going to begin to melt as we add heat. Once all the ice is melted, then the liquid will start heating up until we get to 100 degrees, and then the liquid is going to start to vaporize. Okay, so does that make sense? We're already at 0 degrees. We don't have to heat up the ice to get to the melting point. In the example that we did last week, we had to start even earlier and heat up the ice to 0 degrees, but we're already at 0 degrees, so the ice is immediately going to begin melting as we add heat. Okay, once it's all melted, the temperature is going to begin to rise until we get to 100 degrees, and then the liquid will start vaporizing. So we have to calculate the heat at this step, how much heat is expended to melt the ice. We have to calculate the heat that's expended to raise the temperature, and then we have to calculate the heat that's required to vaporize the liquid. So we have 3 different steps, 3 different pieces where we have to calculate the heat. Okay, so let's start with step 1, and this is the heat required to melt the ice. Okay, so it's a phase change. So we're going to use our latent heat formula. All right, so remember our latent heat formula is Q equals mL. We need to determine, do we want to use the latent heat of fusion or the latent heat of vaporization? So here we're going from a solid to a liquid as we melt. That's fusion, okay? So the heat required to melt all the ice is the mass times the latent heat of fusion, okay? So our mass of the sample, it told us, was 300.0 grams. Our latent heat of fusion is 334 joules per gram. If we do that math out, we should get 100,000 joules. And I'm going to take a little cheat. I need 3 significant figures here, okay? So I'm just gonna underline my significant instead of taking the time to write this in scientific notation. Because 334 has 3 significant figures, my answer should have 3 significant figures. So I'm just going to underline those 3 to remind me that these 3 are significant. Okay, so to go from here to here to melt all of the ice, it requires 100,000 joules of heat. Okay, now how many joules of heat does it require to raise the temperature of the liquid from 0 to 100 degrees? Well, because we're not in a phase change anymore, we use the equation Q equals mc delta T. Okay, we know our mass hasn't changed, still 300.0 grams. We know the specific heat capacity of water, that's our 4.184 joules per gram degrees Celsius. Do we know our temperature change? Well, yeah, the final temperature is going to be 100. We started at 0, so 100 minus 0 is 100.0 degrees Celsius. Okay. If I do this out, I end up with 125,500 joules. So to raise the temperature of the liquid water from 0 to 100, it takes 125,500 joules of heat. And then finally, how much heat do I need to add to vaporize the sample? So this is the heat required to vaporize the water. So again, we use the latent latent heat formula, okay, which is our Q equals mL. This time, because we're moving from a liquid to a gas, we're going to use the latent heat of vaporization. Again, my mass didn't change, 300.0 grams. My latent heat of vaporization is 2,260 joules per gram. And if I do that math, I end up with 678,000 joules. And this zero, again, is significant. Okay. So 100,000 joules to melt the ice, 125,500 joules to heat the melted ice from 0 to 100, and then 678,000 joules of heat to vaporize the sample. So how much total heat was required? I just add all these together. So I have 100,000 joules, 125,500 joules, and 678,000 joules. Okay, so if I add these up, I get 7, 10, 6, 7, 903,500 joules. Okay, now I just need to look at significant figures. So my 100,000, this was the last, the thousands is the least precise. This number, the hundreds position is the least precise. This number is the hundreds position is the least precise. So out of all these, I can only go to the thousands position. So this then I'm going to round to 904,000 joules. And that would be my final answer. Okay, so problems like this, you just have to think, what are all the steps required to get from point A to point B? We started with ice at 0, so we had to melt the ice. Then we had to heat the liquid water up to 100 degrees. Then we had to vaporize the liquid. So we had 3 different steps where we had to analyze how much heat was required and just added them up. Okay, finally, then we talked about exothermic and endothermic reactions. Remember, an exothermic heat is exiting or it's released. Okay, and when that happens, it's going to feel hot. Okay. An endothermic reaction, heat is being absorbed. So it's going to feel cold. All right. Hopefully you watched the videos, had some kind of cool examples of these two things in the lab. We also talked about kinetic energy and potential energy. Kinetic energy and potential energy. If you take physics with me next year, we'll talk a lot about these two things. Okay, so kinetic energy is energy in motion. Potential energy is stored up energy. Okay. The book described in chemistry, energy is stored in the chemical bonds. Okay, we're going to talk a lot more about this in the next module. But just realize that potential energy in chemistry, that energy is stored in those electric bonds. So in an exothermic reaction, we have potential energy being converted to kinetic energy, okay? Some of these bonds are being broken, the energy is being released and used, the energy is in motion. In an endothermic reaction, we have kinetic energy becoming potential energy. So energy is being taken from the surroundings, bonds are being created, and we're ending up with more potential energy, less kinetic energy. We'll talk about these more in the next chapter. And I think that finished out module or chapter 13. So hopefully that review helped, and on the next video we'll move on to new material in chapter 14.